So, my dear student, this video is related to one more important topic of solution chapter. Topic is vapor pressure of liquid solution. In a liquid solution, both solute and solvents are in the liquid state. So in this chapter we will discuss about the vapor pressure of liquid solution. Regarding vapor pressure, we were discussing in class 11 in chapter number 5, state of matter. So vapor pressure of a liquid, it is the pressure applied by the vapor molecules on the surface of a liquid is called vapor pressure. Vapor pressure of a liquid, different liquids have different vapor pressure. Vapor pressure of a liquid depends on temperature as well as intermolecular forces of attraction between the liquid molecules. When temperature increased, vapor pressure of a liquid is increased. When intermolecular forces of attraction between the liquid molecules increases, then vapor pressure of a liquid decreases. So vapor pressure of a liquid is directly proportional to the temperature. When more and more heat is supplied to the liquid, then temperature of the liquid is increased, then rate of vaporization is increased, then number of vapor molecules, then number of molecules in the vapor state increases, then vapor pressure also increases. But vapor pressure of a liquid is inversely related to the intermolecular forces of attraction between the liquid molecules. When liquid molecule to liquid molecule intermolecular forces of attraction is strong, then for that liquid rate of vaporization is low. When rate of vaporization is low, then number of molecules in the vapor state is low, then vapor pressure is also low. So vapor pressure of a liquid depends on temperature of the liquid and intermolecular forces of attraction between the liquid molecules. So vapor pressure is related to that type of liquids which is volatile in nature. So what type of liquids are called volatile liquid? Those liquids are called volatile liquid when they are vaporized on heating. जिस लिक्विड को हीट करने से वेपराइज होता है, that liquid is called volatile liquid. So this topic is related to volatile liquid solution. In this solution, both solute and solvent are volatile. And related law to this topic is Raoult's law. Raoult's law, one of the important law related to the liquid solution. So to explain about this law, let us consider a volatile liquid component 1 in a container. Let us consider a volatile liquid component 1 here. 1. Let us consider this is a volatile liquid component 1 in this container. This is the volatile liquid component. Suppose heat is supplied to this container. Heat supply किया गया. Then molecules of liquid are vaporized from the surface of the liquid. They will vaporize. From the vapor state, molecules are applying pressure on the surface of the liquid, which is known as vapor pressure. So this container is containing only pure component 1. So vapor pressure for the pure component 1 is denoted by P1 naught. Naught represents here pure component. Container is containing only one component. Therefore it is the pure component. The vapor pressure for the pure component 1 is P1 naught. Similarly, one more container in which we are considering a volatile liquid component 2. Component 2 also volatile liquid. So हम लोग यहाँ भी heat supply किया, then molecules are vaporized from the liquid state to the vapor state. From the vapor state, molecules are applying pressure on the surface of the liquid. So vapor pressure for the liquid component 2, let us consider P2 naught. So remember it, naught represents the pure component. Now one more container, this is the third container. This is the third container in which we are considering a solution, or this is a binary solution in which two liquid components are present, component 1 and component 2. So we are preparing a solution by the mixing of two liquid components, liquid component 1 and 2. So यहाँ भी हम लोग heat supply किया, heat is supplied to this container, then both liquid component 1 and 2 are vaporized, both component 1 and 2 are vaporized, then pressure applied by the vapor molecules 1 as well as pressure applied by the vapor molecules 2. Let us consider vapor pressure due to the component 2, let us consider P2, as well as vapor pressure due to the component 1 is considered as P1. Why not is written here? Because these are not two pure component here, 1 and 2 mix kar diya, so it becomes a solution, it becomes a mixture. So vapor pressure due to the component 2 is P2 and vapor pressure due to the component 1 is P1. So here, where in this solution, let us consider mole fraction for the component 1 is x1 and mole fraction for the component 2 is x2. Mole fraction means concentration of the component 1 in this solution x1, और मोल फ्रैक्शन फॉर द कंपोनेंट 2 इज x2. हम लोग कंपोनेंट 1 एंड कंपोनेंट 2 दोनों का कंसेंट्रेशन हम लोग कौन सा यूनिट में कंसिडर कर रहे हैं? मोल फ्रैक्शन में. सो इन द लिक्विड मिक्सर, mole fraction for the component 1 x1, mole fraction for the component 2 x2, and vapor pressure due to the component 2 P2 let us consider, and vapor pressure due to the component 1 is P1. So in this diagram where P1 naught, this is known as vapor pressure for the pure component 1. Similarly, P2 naught, vapor pressure for the pure component 2. And what is P1? P1 is known as partial vapor pressure for the component 1 in the solution. And what is P2 naught? P2 naught is partial vapor pressure for the component 2 in the solution. So according to the Raoult's law, for a volatile liquid solution, according to the Raoult's law, for a volatile liquid solution, partial vapor pressure of each component is directly proportional to the mole fraction of it in the solution. So this is the statement of the Raoult's law. So according to the Raoult's law, for a volatile liquid solution, Raoult's law is applicable for volatile liquid solution only. It is related to, Raoult's law is related to only volatile liquids. So according to the Raoult's law, for a volatile liquid solution, partial vapor pressure of each component is directly proportional to the mole fraction of it in the solution. That means in this solution partial vapor pressure for the component 1 depends on the mole fraction of component 1 in the solution. Similarly, partial vapor pressure P2 for the component 2 is directly related to the mole fraction of component 2 in the solution. That is, P1 directly proportional to X1. Similarly, P2 directly proportional to X2. When X1 increases, P1 increases. When X2 increases, then P2 also increases. So vapor pressure of each component in a solution is directly proportional to the mole fraction of it in the solution. This is the Raoult's law. So according to Raoult's law, for component 1 in the above solution, P1 directly proportional to X1. Proportionality sign is removed by putting a proportionality constant P1 not into X1. What is P1 not? P1 not is the vapor pressure for the pure component 1. So this is the mathematical form of the Raoult's law for the component 1 in a liquid solution. Similarly, for the component 2, vapor pressure due to the component 2 in the above solution P2 directly proportional to X2, then P2 equal to P2 naught X2. So what is P2 naught? What is P2 naught? P2 naught is the vapor pressure for the pure component 2. So this is the mathematical form of the Raoult's law for the component 2 in the above solution, or this is the mathematical form of the Raoult's law for the component 1 in the above solution. Now according to Dalton's law of partial pressure, total vapor pressure in the above solution P total equal to P1 plus P2. So according to Dalton's law of partial pressure, regarding Dalton's law, we were discussing in state of matter chapter in class 11. So according to Dalton's law of partial pressure, total vapor pressure P total equal to P1 plus P2. So P1 equal to P1 naught X1 and P2 equal to P2 naught X2. Now in place of X1 we can put 1 minus X2 and P2 naught into X2, since X1 plus X2 equal to 1. If X1 plus X2 equal to 1, then X1 equal to we can write 1 minus X2. So X1 का जगह में हम लोग क्या लिखा है 1 minus X2. Then multiply करना है P1 not into 1, P1 not, then ये multiply करने से P1 not X2 plus P2 not X2. Now P1 not पॉजिटिव को आगे लिख रहा है, हम लोग नेगेटिव को पीछे कर रहे हैं. Then P1 not X2 we can take common, so P2 not minus P1 not into X2 not. So this is one of the relation to find out total vapor pressure of a liquid solution. So to find out total vapor pressure of a liquid solution, what are the values are needed? X2 is needed. What is X2? X2 is the mole fraction for the component 2 in the solution. And P1 is needed. What is P1? P1 not is needed. What is P1 not? P1 naught is the vapor pressure for the pure component 1, and P2 naught also needed. What is P2 naught? P2 naught also vapor pressure for the pure component 2. So this is the mathematical relation to find out total vapor pressure of a solution. Let us now graphically represent the Raoult's law. So let us, if x1 equal to 1, then obviously x2 equal to how many? 0. Why? x1 plus x2 always equal to 1. That means if x1 equal to 1, x2 equal to 0. If x1 equal to 0, then x2 obviously equal to 1. So if x1 equal to 1, then P1 equal to P1 naught, and P2 equal to 0. If x1 equal to 1, P1 equal to P1 naught, and if x2 equal to 0, P2 equal to 0. How? P1 equal to P1 naught, since P1 equal to P1 naught x1, and P2 equal to 0 when x2 equal to 0, P2 equal to 0, since P2 equal to P1 naught x2, P2 naught x2. Similarly, if x1 equal to 0, then obviously x2 equal to 1. If x1 equal to 0, then P1 also equal to 0. If x2 equal to 1, then P2 equal to how many? P2 naught. So this is the graph in which vapor pressure is plotting against the mole fraction. This is the graph. This is one of the extreme point at which x1 equal to 1 and x2 equal to 0. This is the condition here. This one the condition at this point, and at this point x1 equal to 0 and x2 equal to 1. That means this is the condition. This is the condition at this point. If x1 equal to 1, x2 equal to 0, that means at this point container is containing only liquid component 1. Liquid component 1 only present at this point. Liquid component 2 is not here. That means container is containing only pure component 1. Let us consider due to the pure component 1, vapor pressure is P1 naught. यहाँ से यहाँ तक this is the vapor pressure for the pure component 1. Vapor pressure for the pure component 1 is considered as P1 naught. जब हम लोग लेफ्ट टू राइट मूव करेगा, x1 धीरे धीरे डिक्रीज होगा, डिक्रीज होके x1 becomes 0 at this point, and x2 धीरे धीरे इंक्रीज होगा, और x2 इंक्रीज होके it becomes x2 equal to 1 से ज़्यादा नहीं हो सकता है, क्योंकि x1 plus x2 always equal to 1 in a binary solution. So at this point, at this point, component 1 is absent in the container. Component 1 नहीं है कंटेनर के में, क्योंकि component 1 के लिए मोल फ्रैक्शन कितना है? 0. ये पॉइंट में only component 2 प्रेजेंट है. That means कंटेनर में only pure component 2 प्रेजेंट है. So vapor pressure हम लोगों को मिलेगा only pure component 2 के लिए. So let us consider vapor pressure for the pure component 2 is P2 naught. Let us consider P2 naught value is higher than the P1 naught. क्यों? क्योंकि कभी भी दो प्योर लिक्विड का वेपर प्रेशर इक्वल नहीं हो सकता है, क्योंकि वेपर प्रेशर ऑफ ए लिक्विड डिपेंड्स ऑन द इंटरमोलिकुलर फोर्सेस ऑफ अट्रैक्शन बिटवीन द लिक्विड मोलिकुल्स. सो डिफरेंट लिक्विड में intermolecular forces of attraction between the liquid molecule is different. So P1 naught is smaller than P2 naught. That means liquid component 1 में molecule to molecule intermolecular forces of attraction strong है, और component 2 में pure component 2 में हम लोग क्या consider किया, molecule to molecule intermolecular forces of attraction weak है, इसलिए P2 naught higher than the P1 naught. So X1 left to right धीरे धीरे decrease हो रहा है. So let us draw a line here to here. One more line. This is straight line. So when X1 decreases from left to right, when X1 decreases, then P1 also decreases. जब लेफ्ट टू राइट X1 डिक्रीज होगा, P1 भी डिक्रीज होगा, लेकिन P1 कितना से डिक्रीज होगा, P1 नॉट से. सो ये ग्राफ, दिस ग्राफ रिप्रेजेंट्स द राउल्ट्स लॉ. दिस इज द राउल्ट्स लॉ. दिस ग्राफ रिप्रेजेंट्स द राउल्ट्स लॉ फॉर द कंपोनेंट 1. मतलब ऑन दिस ग्राफ P1 इक्वल टू P1 नॉट X1. जब X1 धीरे धीरे डिक्रीज हो रहा है फ्रॉम लेफ्ट टू राइट, P1 डिक्रीजेस फ्रॉम P1 नॉट, और जब X1 यहाँ 0 हो गया, P1 becomes how many? 0. So this is the line, or this line represents the Raoult's law for the liquid component 1 in the solution. And from left to right, X2 increases. When X2 equal to 0, P2 also equal to 0, क्योंकि X2 directly proportional to P2. When X2 0, P2 0, X2 0, P2 0. When X2 increases, P2 also increases. So when X2 increases, P2 increases. So this is the line which represents the Raoult's law for the component 2. So X2 increase होके ये एक्सट्रीम पॉइंट में X2 कितना हो गया, 1 हो गया, X2 मैक्सिमम हो गया, इसीलिए एट दिस पॉइंट P2 becomes P2 naught. So this line represents the Raoult's law for the component 1, and this line represents the Raoult's law for the liquid component 2. और ये दोनों पॉइंट को हम लोग जब ज्वाइन कर देता है, then we have total vapor pressure of liquid solution. So this is the graphical representations of Raoult's law for a volatile liquid solution. Again, consider a liquid solution. Two liquid component here, component 1 and component 2. In this liquid solution, mole fraction for the component 1 X1, mole fraction for the component 2 X2. So X1 and X2 are the composition or mole fractions of component 1 in the liquid phase, and Y1 and Y2 are the composition or mole fractions of component 1 in the vapor phase. Y1 mole fraction for component 1 in the vapor phase, and Y2 mole fraction for the component 2 in the vapor phase. So Y1 and Y2 are the composition of component 1 and 2 in the vapor phase. X1 and X2 are the composition of component 1 and 2 in the liquid phase. So how can you calculate now Y1 and Y2? How can we calculate? So relation to to calculate composition y1 and y2 in the vapor phase are P1 equal to y1 into P total and P2 equal to y2 into P total. So these are the. So to clear your concept, solve example 2.5, not exercise, it is example, it is already solved in your textbook. So you solve again this example 2.5 from your textbook, then your concept will clear. So thank you.